in the last video for this particular lecture module series, I wanted to define what is an even function and what is an odd function and what are the ways that we can determine that. So right off the bat, before we get into it, even and odd functions have nothing to do with even numbers and odd numbers. Now, there technically is a connection when it comes to polynomial degrees, because there is a correlation between even degree and odd degree being even and odd, but I'll circle back to that in a minute. So let's start with, well, what is an even function, what is an odd function, and how do we define that? So I wanted to start with the mathematical definition because it can be a little bit confusing, and then we'll look at some graphs to sort of see the idea of what this means, and then we'll talk about how we can actually verify even and oddness algebraically, because that's how you really prove that something's even or odd. But by definition, an even function satisfies the condition that f of minus x is equal to f of x. And so this can be kind of a hard thing to really read and understand unless you're super used to dealing with function notation. But if you throw a number into it, it can kind of help you understand what this definition is getting at. Let's just say I plug in 2 arbitrarily into this definition. And if it's an even function, it must satisfy this for all x values. And so I'm allowed to plug in 1 if I want. It's not going to tell me anything, it's just going to give me an idea. But basically what it's going to say is f of 2 is equal to f of minus 2, or vice versa. And basically if I'm thinking about that, what would be, remember that x is going to be the input value. So whether it's 2 or minus 2, it says that the function's value or the y value is going to be equal on both sides. So if I was to recreate a graph of what that's going to look like, well, let's just say it makes 5 arbitrarily. Well, basically whether it's 2 or minus 2, the value would have to be the same on both sides. Again, I'm just picking 5 at random because I don't know a function, I'm just making something up. So basically whether I'm on the right side or the left side, we're going to have the same height value. And let me do that a little bit better and try to be pretty accurate with my height, because it's supposed to be 5 on both sides and 2 versus minus 2. And let's say f of 1 is 0. Well, at f of minus 1, it would also have to be 0 if it was even, because no matter where you are, f of x must be equal to f of minus x. And say your f of 3 is 2. F of minus 3 would also be 2. So on the right side, if our graph looks something like this, on the left side, it's also going to have the same graph. And this is kind of the visual symmetry you would have. And I don't know what it would do in between, but on both sides of the curve, you're going to have the same shape regardless. And this is a sort of symmetry you probably recognize from various different graphs in mathematics. But this is what we refer to as symmetry when it's the same on the right and left-hand side. Or you might think of it looks kind of like a mirror image. If this graph was looking in the mirror, it would see exactly the same thing, but backwards. And we refer to it as being symmetric with respect to the y-axis because that's like the mirror in this case, the reflector, where if you go across the y-axis, it's the same distance on both sides from every point to the next. And anyways, so the whole point of all that was to sort of examine what symmetry looks like and what that definition really means and how I can view it. But let's say we were looking at the graph of a function, say f of x is equal to x squared. Now you might remember what that looks like because it's a very basic square function, and all quadratics or degree 2 polynomial functions always look like parabolas. And we're going to talk a lot about that next week. But I could always stick it in my graph to see, but when I'm looking at that, I can see f of x squared. Well, it's the same on both the left-hand side and the right-hand side. Not the same, but you know what I mean. Again, the proper mathematical term is it is symmetric with respect to the y-axis, because each side reflects across itself. And parabolas, assuming that they have not been translated to the right or to the left, are always symmetric, assuming that they're focused right there on the y-axis. And so again, we would call this function even because that's the symmetry that an even function exhibits, the same on both sides. Now an odd function is very, very similar with one notable key difference. It says odd functions satisfy the condition that f of minus x is equal to negative f of x. And that's the only difference between even and odd, is that if you're going to plug in a negative versus a positive, it says that there's also an additional negative sign. So if I was thinking about the same definition as before, if I was to look at f of -2, but the function were odd instead, so let me actually erase the right-hand side over here because this is the one thing that's going to change. If it were odd, is that f of -2 would not be equal to f of 2. F of 2 would be equal to negative f of 2 because it has an extra negative sign. So, and also that would mean that if it were equal to 5, it would be equal to, f of 2 would be equal to -5 because notice what I just wrote doesn't make any sense. But if I were to apply, whoops, I'm hitting undo in the wrong way. So again, let me try to, I'm saying this in a confusing way. Let me rethink this. If f of 2, -2 is equal to 5, then what it says is that, why is my pen not working? Okay, here we go. F of -2, if f of -2 is equal to 5, then it should be equal to negative f of 2, which is implying it should be equal to negative whatever f of 2 is. And since 5 is obviously not equal to -5, that means f of 2 would have to be -5, because the only way to make a negative f of 2 be equal to a positive is if it were a double negative. So that was really confusing probably, I'm sorry. The summary is that the sign will be opposite when it's reflected. So if f of -2 is 5, f of 2 will be the opposite signed answer, because right, that's what a negative means, the exact opposite or upside down. So basically that point would be down here instead. And let's say that f of -3 was equal to 2. That means that f of 3 would be equal to -2 instead. And what would happen is all those points would be the same. They would just be upside down instead based on the curvature. And so this is the sort of symmetry, and again, this sketch is not perfect, that an odd function exhibits. When it's not just reflected about the y-axis, but when it's reflected, it is also made upside down. So I kind of see this part, if it was just reflected about the y, it would look like this. But now that part has been flipped upside down as well. So it's been both reflected across the y-axis and the x-axis. And then this part, again, if that were reflected, it would look like this, but that has been now moved upside down. And this part would look, something like that. Again, now upside down instead. So it's been flipped over and turned upside down. And some books refer to this as being symmetric with respect to the origin. I think our book says that, which is not really correct, because symmetry with respect to the origin usually looks a little different. It depends on how you define it, but I like to just say it's symmetric about both the x and y axes combined. But again, some people would say that it's wrong depending on how you're viewing that. It's not that important. Anyways, this is kind of what an odd function looks like. And let's look at the next example, B, which is called the reciprocal function, which is just 1 divided by x. This is an example of an odd function, and if we go ahead and toss that into our graph, I'm going to zoom in on this by 1 tick just so I can get a better view of it. Notice that, actually let me just zoom standard on it, and then I'll zoom in. Notice that on the left-hand side and the right-hand side, it's clearly not exactly the same thing on both sides, but the shape is the same. It's upside down and it's opposite, right? Because if I were to reflect it this way, it would look something like this across the y-axis. And then if I also reflect it across the x-axis, what I would get is exactly this shape. So it gives us this sort of reflected shape across both x and y. So it's both flipped over and upside down. Another way I like to say is it's sort of like turning the page. What does it look like over here? And then I'm turning the page this way across the x. And summary, that would be what an odd function would look like. It's always symmetric about both x and y. So you could think of it as being flipped over and upside down, odd. So that's long enough for this video. Check out these next two yourself to see if you can determine whether they are even or odd graphically. There is another way to do it too, basically by using algebra, and we'll talk about that process in the next video.